So in the last video, when I introduced you into solving solving ordinary differential equations using the Laplace transform, we had it a lot where this plus this was equal to 0, or this minus this was equal to 0, and we could kind of set some things equal to each other, and it was a bit easier because a lot of them involved exponential functions, right? Because, for example, we had one where it was d squared x minus d cubed x was equal to 0, and we had some initial conditions, and we knew that this would just be an exponential because the derivative of one minus the other is just 0 because they're equal to each other. But let's do one here where that's not the case. Let's say the derivative, first order derivative, minus the function itself is equal to 3 sine t. So this is a bit harder because it's going to be very difficult to kind of think of a function where we take the derivative of it, we subtract the function itself, and we get 3 sine t. Okay, so we're going to actually have to solve this. We can't just do it in our head. Okay, and I don't know why I erased it. I'm going to say initial conditions. We can say, I'll just make it easy, x of 0 equals 0. So we only need one initial condition because we only have a first order derivative. So whatever order you're taking the derivative of, you need that many initial conditions. So this one here, it's a first order, we only need one initial condition here. So the Laplace transform of d of x minus the Laplace transform of x equals, it's linear, so we can take out this 3, so 3 Laplace transform sine t. Okay, now we know that with first order derivatives, it's going to be s times L of x minus the initial condition, which is 0, so we don't even need to write it. Then we can go minus L of x. That doesn't change, right, because now these are both L of x, which is going to be good. And that's going to be equal to 3 times the Laplace transform of sine of t. And remember, with our chart, that's just 1 over s squared plus 1. Okay, so now we're going to have, I'll just actually distribute this 3 into the top, so it'll be 3 over s squared plus 1. And if we were to factor an L of x out here, we'd get L of x times s minus 1 equals 3 over s squared plus 1. So we'll get that the Laplace transform of our function x. When we take the transform of it, we're going to get 3 over s minus 1 times s squared plus 1. So remember, whenever we have some weird function with fractions and lots of factors on the bottom of the fraction, we're going to go with our partial fraction decomposition. Okay, so in this case, we have a linear term and we have a quadratic term, so to the power of 2. So that means that we're going to say 3 over s minus 1 times s squared plus 1. This is what we're starting with. This is our Laplace transform right here. We're going to say that's going to be equal to some constant a over the linear factor s minus 1. And remember, when there's a quadratic factor on the bottom, we have to go plus bs plus c. So it's going to be a linear term on the top over s squared plus 1. And the reason for that is this is a degree 1 term on the bottom for s minus 1. This is a degree 0, so it's 1 less. This is a quadratic term, so it's s squared. And this is a linear term, which is 1 less. So the term on the top has to be a degree less than the one on the bottom. And anytime this is a linear term, we always have a plus c here because we can't assume it's 0, right? It could be something else. So if we multiply both sides by this denominator here, we're kind of used to this by now. We get 3 equals a times s squared plus 1. Plus, we're going to get bs plus c times s minus 1. Okay, and now that we have that, let's just kind of expand this out, and then we simplify. We're going to get 3 equals, why does it do that? As squared plus A plus BS squared plus CS, so I'm just kind of expanding all these terms here, minus BS minus C. Okay, and let's just kind of group these S squareds together. Let's group the S's together and the constants together. So when we do that and we kind of factor all that we can, we're going to get 3 equals, so if we have the S squareds here, there's an A and a B with an S squared, so it'll become A plus B. So let's take care of these two terms. Now we want to have our plus S, and now it's a CS minus BS if we go MC minus B. Right, and then we just have plus A minus C there. Okay, so we know that's equal to 3. So remember with partial fraction decomposition, we try to get certain terms equal to 0. So, let's see here. This left side here, it's a constant. So if it's a constant, that means it's not reliant on S. No variables are involved. So see how these first two terms here, they have an S? That means that they can't exist, meaning A plus B has to be equal to 0, and C minus B has to be equal to 0. So if A plus B equals 0, that means that this S squared just disappears, and if C minus B equals 0, that means that this S term just disappears, because it's the variable times 0. No matter what the variable is, we're just going to get 0, leaving us with A minus C has to be equal to 3. Right, because A minus C are the only constant terms that aren't reliant on some variable. Okay, so now if we just kind of isolate for one variable, we're going to get that A equals negative B, C equals B, and A equals 3 plus C. Okay, since 3 has no variables. And then solving, right, we have 3 variables, we have 3 equations. If A is negative B, well, that means that C equals negative A, because B is just negative A. And if C is negative A, well, this must mean that negative C equals 3 plus C. So then we're going to subtract 2 on both sides. Yeah, we're going to subtract on both sides, so negative C equals, negative 2C equals 3. And if we divide by negative 2 on both sides, we're going to get C is negative 3 over 2. And since C is negative 3 over 2, and it's also equal to negative A, we just take the negative of that, so A is equal to positive 3 over 2. And if A is equal to negative B, that means that B must be equal to negative 3 over 2 as well. So we didn't even need to solve other than that, because by setting all of these equal to 0, we just got rid of them, and it kind of added to our system of equations. We could solve it a bit quicker. Okay, so that was definitely a good way of doing it, and now we can kind of plug these constants back into our equation. So we're going to get, we kind of L of x, this is our partial fraction decomposition. We're splitting it up into multiple fractions here. We're going to get 3 over 2 over s minus 1. So remember, this was our a over s minus 1. I'm going to go minus 3 over 2s. So this would be our bs term, right? Because b is negative 3 over 2, and then s is just s. It's multiplying in there. S squared plus 1. And originally it was bs plus c, but we can split that plus c into a different term itself with the same denominator as the bs. So this one's also going to be minus 3 over 2. So it's going to be minus 3 over 2 over s squared plus 1. Okay, cool. So now that we have three things kind of split up into different terms, we can take the inverse across of everything. So I'm going to factor out this all the 3 over 2s. So x will be 3 over 2 times the inverse Laplace of 1 over s minus 1 minus 3 over 2 inverse Laplace of s over s squared plus 1 minus 3 over 2 inverse Laplace, hopefully this fits, 1 over s squared plus 1. Okay, so we got a bunch of 3 over 2s going on here, some inverse Laplace transforms. Now let's use our table. So we know that the inverse Laplace of 1 over s minus 1 by now is just e to the t. So this is going to be 3 over 2 e to the t. So if you know that right off the bat, you don't need to check the table. And s over s squared plus 1, well, let's take a look at our table for that. So the inverse Laplace, s over s squared plus 1, that's going to be this guy right here. So we know it's going to be the cosine function. If it's s over s squared plus 1, well, that 1 is acting as our b squared. So to find b, we just square root it. And the square root of 1 is just 1 itself. So it's going to be the cosine of 1t, or just the cosine of t. So minus 3 over 2 cosine of t. Okay. And then the last term here, 1 over s squared plus 1, it's the same thing, except it doesn't have the s on the top. And when it doesn't have the s, that's going to be a sine function using our table. So it's going to be 3 over 2 sine. And this is also going to be 1t, because this is s squared plus 1. Square rooting, we just get 1. So this is the answer to our differential equation right here. And like we did in the last video, to check if we're right, we can always kind of apply the initial conditions and solve the equation ourselves. So we know that x of 0 is equal to 0. Let's just plug that in. So 3 over 2 e to the 0 minus 3 over 2 cos 0 minus 3 over 2 sine 0. Well, 3 over 2 e to the 0 is 3 over 2 times 1, so 3 over 2 minus cosine 0 is 1, so minus 3 over 2 times 1, and then minus sine of 0 is 0, so this is going to be 0. So yeah, the initial condition does check out there. And let's just kind of double check that dx minus x equals 3 sine t. So the derivative of this is going to be 3 over 2 e to the t. The derivative of cosine is negative sine, but then this is a negative cosine, so it's going to become positive. So plus sine t, or it's going to be 3 halves, sorry, so plus 3 halves sine t. And then we have the derivative of negative 3 over 2 sine t. So that's going to give us negative cosine. So it'll be minus 3 over 2 cosine t. And then when we're subtracting just x itself, minus 3 over 2 e to the t. And then we got 3 over 2 cos t minus 3 over 2 sine t. Okay, so what we're doing now is we have 3 over 2 e to the t minus 3 over 2 e to the t, so that's going to go away. 3 over 2 sine t minus negative 3 over 2 sine t, so that's going to be adding. So 3 over 2 sine t plus 3 over 2 sine t. And then we have negative 3 over 2 cos t minus negative that, so we're going to get 0 back. It's like negative plus 1. So when we have 3 over 2 plus 3 over 2, this is like 6 over 2. Well, we just sort of 3 halves plus 3 halves. When 2 halves come together, they become 1, so it's just 3 sine t. So all of our conditions are met, which is great. Always nice to see that after you solve a bit of a lengthy differential equation. Always a good feeling. Makes you feel like you learn more. So that was a bit of a harder one from the one we did before. And in my next one, I'm probably going to do, I'd say it's the hardest math question I've ever kind of written down. It's the longest for sure, so we can look forward to that, and I'll see you there. I'm excited.